Hi, my name is François and I will be presenting Foldover-free maps in 15 lines of code. The code and much more is available at the GitHub link at the bottom of the slide. This work is a joint effort between the GridJet team from Moscow, Russia, and the Pixel team from Nancy in France. The goal of this talk is to compute maps without foldovers. Let's see what it means. The construction of maps has a rich history, as they are a vital tool to locate and study your surroundings. Mathematically, they represent a transformation from a domain, here the surface of the Earth, to another domain, the square on the plane. We denote the transformation u of x and its inverse, x of u. For a given map, we expect two main qualities. First, bijectivity. There should be a non-ambiguous correspondence between the map and the object. And second, control of the distortion. It means that we should be able to use the map. For example, if I want to measure distance between Nancy and Los Angeles, the Mercator map might be decent, as shown on the left, but another map, as in the right, would be very bad. Our work mainly focuses on bijectivity, but still bring a decent solution for the control of the distortion. Now, in computer graphics, we commonly have a surface, triangulated, that we map to the plane. It means that U becomes a transformation on each triangle that is locally applied on nodes of the triangulation. We can note two things. First, the transformation here is linear on each triangle, which is very handy. And secondly, we need, for it to be bijective, we need its determinant, so the determinant of the Jacobian matrix of the mapping, to be positive. Those maps are very useful in computer graphics. They are used, for example, in shape correspondence, texturing, or even remeshing. The most common tool to compute such maps is the Tet Embedding, introduced by Tet in 1963. The idea is that we take a domain and map its boundary to another domain, and then we move each point in the middle of its neighbors. What we have is that if the boundary domain is convex, then we are guaranteed to obtain a good mapping. The issue is that if it is not convex, we don't have any guarantees. And even worse, we can go from a mapping that is valid, use the Tet embedding, and obtain an inverted mapping. Another issue is that it doesn't translate to 3D. What we hope for is to have an energy that if we find the minimum of this energy, we obtain a valid mapping. The recent trend is to use a mix of two energies. The first one, which is a shape distortion energy, and the second one, which is an area distortion energy. We combine those two and obtain an energy, E, which is a polyconvex energy, which means that it is a well-posed problem, which comes from hyperelasticity theory. Our energy contains a lambda that we can use to obtain very different behaviors. For example, if I take this rest shape, I can deform it by taking the red points and moving them. If I put the lambda as 0, I will obtain a conformal mapping, where angles are preserved. But if I put the lambda as quasi-infinite, I will obtain a mapping which tries to conserve the area of the triangles. What we use in the paper is the lambda equals to 1, which gives a quasi-isometric mapping. And we can use it to do stretch, compressing, or even bending on our model, and our results are very elasticity-like. A key feature of f and j is that we divide by the determinant. This means that if we start with a non-inverted element, the energy possesses a barrier which will prevent any elements from inverting, as shown in the plot. To guarantee that the energy will behave accordingly, what we do is we put the energy as infinite if the determinant is negative. As a notation, we replace the determinant by the max of 0 and the determinant. This gives us a modified version of f and j with, at the denominator, the max of the det of j and 0. This energy behaves very well, and it is, to our knowledge, the best energy to use to obtain a quality mapping. But using this energy, we immediately get to a problem. The idea that if we can't get an initialization that has a positive determinant, it means that we can't optimize because our energy is infinite. And in some application, it will happen because we have very difficult domain to map and there is no good guesses. Addressing this problem is a very active research topic. We can mention two works in this way. The first one, simplex assembly, disassemble the triangles to obtain a valid triangle, and then slowly reassemble them while optimizing the energy E. Another one is total lifted content, the most recent paper on this topic, which tried to minimize the unsigned area of the simplices to obtain a valid mapping, and then uses a standard energy to obtain a quality mapping. Other works will rely on very difficult problem to optimize. What we propose in our paper is an energy that first is defined continuously, meaning that we don't work on tricks on simplices. Moreover, it directly works on the energy E. So we are going straightforward to a nice solution. And finally, it is way more robust than the state of the art. To obtain such results, the idea is that we use a regularization, and with it, we bring a lot of very good theoretical guarantees. The main idea is to take the problematic max and to replace it by a function xi. And this xi, which depends on the determinant and an epsilon, is going to match slowly the maximum when the epsilon is slowly going to 0. We then can replace the maximum by this xi in the expression of f and j, and we obtain a new energy, which we call E of epsilon, which when we slowly minimize the epsilon is going to tend to our original energy. So the topic now is to how can we create a sequence of epsilon from which we can optimize our energy. Before seeing how to minimize the energy, let's see how it behaves. We take a mesh, such as this one, and we lock the black points, and the red point is free to move. For a new position of this point, as here in yellow, we obtain the value for the energy, and for another position, another value. What we can do is for each position of this red point, we can plot the value of the energy. If the value is blue, we will be quite happy, the solver will be happy, but if the energy is yellow, it will try to converge to blue position. We plot the energy here for a value of epsilon, but we can take this epsilon and slowly decrease it to see how it will behave. We can see that slowly the blue values are going inside of the mesh, meaning that it is where the value, where the elements are not inverted. We can take a new mesh, a bit more difficult, which is here is not convex, and we can do a similar process. What we can see is while in the first one, all value in the mesh good, in the new one, we are restricted to a small quadrilateral, which does not represent all the mesh. To obtain a valid mapping, the process is very straightforward. We start with an initialization, and then we choose an epsilon, and optimize the energy for the given epsilon. And with a decreasing sequence of epsilon, we slowly minimize the energy such that at the end we obtain a valid mapping. Note that when we have a determinant superior to 0, it means that we are optimizing the energy E as it was defined previously without any epsilon. So it gives a good quality mapping. A few things about the implementation. First, it requires a decreasing sequence of epsilon, so that we guarantee that at the end we obtain a valid mapping. If we take a very small epsilon, it will lead to a very stiff problem to solve. In the paper, we propose a sequence of epsilon, which gives very good theoretical guarantees while still being relatively fast in terms of convergence. Moreover, we provide an implementation using LBFGS algorithm at the GitHub link. Finally, for very stiff problem, we use a part of the Asian which is symmetric positive definite with a Newton implementation. There is more theoretical guarantees in the paper. If you're interested, please check it out. To back up our robustness claim, it is important to test our method in a lot of settings. A very basic test is to take a mesh and invert 2 points. While being a test relatively easy to set up, it can be very difficult to untangle. Our algorithm has no trouble doing it on this case or even in 3D. I don't give the example in 3D because we can do even more difficult. If we take this cube and we remove a cube inside it, then we rotate the inside by an angle of 80 degrees. The initialization mesh is a very difficult one to untangle, but our algorithm does it without any issues. Actually, we can do this test for several different angles of rotation. Here you have the result. At the top, we cut the model in the middle. At the bottom, you get the back of the model. You can see that we are able to untangle all those challenges without too much trouble. Note that in some cases, very stiff, such as the last one, we need to use a Newton implementation, as LBFGS is not sufficient. But currently, the state of the art would struggle at more than 90 degrees, as total lifted content does. With its paper, Total Lifted Content gave a huge database of more than 10,000 challenges, both 2D and 3D. In 2D, most often, you take a domain, surface, and you map it with a Tet Embedding to the plane. The issue is that your boundary is not convex, so you obtain a tangled mesh, and the process is to untangle this mesh. In 3D, the database contains two types of mappings. The first one is deformation, so you take a bar and try to deform it or make the armadillo dance, as shown here. But you can as well map yourself to a convex domain, which in 3D, the Tet embeddings doesn't work. So it's interesting to see if your algorithm is able to obtain a valid mapping in a convex domain, such as the sphere. Our LBFGS implementation is able to untangle all the challenges in very reasonable time. Most of the time, it will take some seconds to. On very stiff problems, it can take several minutes, but not much more. On the plot, you can notice some lines in the 3D part. Well, it is because the database contains a lot of deformation of the armadillo, for example, and the more difficult the deformation, the more time it takes. Now, with the result of this database, let's compare ourselves very precisely to Total Lifted. We take three different initialization. The first one, which is a Tet embedding, the second one, which is collapse all the model to one point, and the third one, which is a random initialization. And we try to map Lucy, the model Lucy, to the P of SIGGRAPH. We can first notice a thing is that Total Lifted Content will not move the point a lot. It is because when the mesh is untangled, Total Lifted Content has a degenerated energy. While in our case, we obtain a mesh that is always the same result, as we are converging to the same solution when epsilon is equal to 0. Another thing is that we are more robust to very difficult initialization, such as a random initialization. To conclude, we can see that our approach is initialization invariant, it can control the distortion while optimizing the untangling, and it is robust to very bad initialization. The paper, we compare ourselves to other approach than Total Lifted Content, but the result is still always the same. We are overall more robust and still control the distortion to the same extent as the literature. Finally, for the limitation of our work, we can mention two things. The first one, as shown on the left, is that in some cases, we can get stuck in a local minima, where the mesh is already untangled, but it is not the global minima of our energy. The issue is that we can't get from one solution to the other solution without untangling again the mesh, which is impossible, considering that our energy would be infinite. We are stuck in what we call a rabbit hole, but well, it doesn't happen in practice, but it is more of a theoretical drawback. The second limitation is what we call K-coverings. The idea is that when dealing with free boundaries, we can get cases where all the elements are not inverted, but around a vertex, just a vertex, we have a degenerated solution, which is a K-covering, meaning that the meshes is turning around the vertex. This happens only when the boundary is free to move, so when we deal with constrained boundary, it doesn't happen, which we recommend in the paper. But sometimes we might require to obtain solution for free boundary in some settings, so it is still a work in progress. And that will conclude my talk. I thank you for your attention, and please, if you are interested, check out our GitHub link.